TUBS-IRMB. Digital India. Educated India.
Welcome to this third lecture about the equilibrium function that Boltzmann obtained from the ESA theorem that we had discussed yesterday. And as a reminder, eta was defined as the integral over the distribution function in the logarithm. So I said, I believe yesterday I wrote log instead of ln. Really doesn't matter. This would only be scaled by a factor. We integrate this over the entire space and over the entire velocity space. So, and then we discovered that the time derivative of this thing is smaller or equal to 0 always. Yeah. So the case that this time derivative is equal to 0, so when no further change is possible, this is what we call the equilibrium. In equilibrium, the physicists will always tell you that the equilibrium is only defined for the entire universe, right? But we could, so here we kind of use this in a more loosely, I mean, we need the equilibrium for the entire universe as an abstract thing to actually see how the thing is looking. But later, we'll deal with what we call the local equilibrium. So we take only a small part of the universe, yeah, and see how that is approaching that. So this, if the universe would only be this small part, yeah, so then it would still have that sort of equilibrium, and this is where this small part of the world is going to, right? This is where we are heading. So, but first of all, we have to determine what this equilibrium actually is. And here yesterday, we derived this. The time derivative of this was 1/4. So we wrote it a different way. We said that 4 times this time derivative is 1/4 the integral with b. B is giving the probability that something hits. So the important thing that I did not say, that b is also a positive function, yeah, because the thing is always negative because b is always positive, right? So if b could be positive or negative, that could give us the entropy going in the opposite direction, obviously, yeah. But b is a positive function, and then we have the population scattered into this state. This is the gain term, and then we have the loss term. This is what is scattered out of the state, and then we saw that we have the logarithm of the pre-collision states and that of the post-collision states, and we have to integrate this over xc1, xc2, all directions, and the entire space. So, and we found that this here is smaller or equal than 0. So, I mean, an integral over a positive function is only 0 when it's 0 everywhere. Yeah, that's the important thing here. Yeah, this means that when we are at equilibrium, so when this is actually the stage, then we have this only if for all the Xi1, Xi2, and also the ones that go out. We have for all these velocities and in the entire universe, we need to have these two things, these two products to be equal, right? Then we are at equilibrium. So we can rearrange this, putting f1 times f2 on the other side, and then we take the logarithm out of this. So you see, this is the same as saying that the logarithm of f1 plus the logarithm of f1, the logarithm of f2 is equal to the logarithm of f1 after collision plus the logarithm of f2 after collision. Yeah, right? You see this. Yeah, it's no problem. So this, and the equilibrium is now a function that only depends on the conserved quantities. And the conserved quantities are in this case mass, momentum, and energy. So there was a conjecture of Maxwell that has been proven by Boltzmann. Boltzmann in 1872, if I'm not mistaken, that this is the case that when the logarithm of the equilibrium can be written as a function with a constant, then something times the velocity, which is related to its momentum, plus something else times the velocity square, which is related to the energy. So then for the left-hand side of equation 3.1 that we had above, this reads that ln f1 plus ln f2 is equal to 2 times a plus b. Now what comes here? So this is the velocity of the first particle and the velocity of the second particle plus c, the velocity square of the first particle plus the velocity square, what am I doing, of the second particle. So these are scalar products. And now you can identify this is the mass. So, okay, I'm using the word mass a little bit loosely here, not really in the physical sense, but more in the mathematical sense. So the probability is, for a mathematician, the mass is the probability that there's something there. Yeah. So the mass of the particle itself is something that we pick out because it is irrelevant. They all have the same mass. So in this rho just means the probability of particles being there, or density of how many are there. So okay, I should write it like this. So this is the momentum. and this is the energy. And then there are no further contributions. And because these are the conserved quantities, the right-hand side of equation 3.1 would look exactly the same. Now we have the logarithm of the distribution after the collision of particle 1 and particle 2. They are not required to be the same, yeah, as before. So the individual F1 or say F2 and F2 dash is not the same, right? It's only their product is the same. Yeah, but this leads to the case that we have here the same thing, but we should have the same thing. So this here is, of course, now the velocity after the collision and giving us the velocity product. Oh, this is not nicely written. So after collision plus C2 after collision. So again, these are not the same velocities. These are not the same velocities here, but their sum is the same. Yeah. So because the collision conserves energy and momentum. So, and since the equilibrium looks like this, we can now take the the logarithm to the exponent, and then we see that we have an e by a power of a, which simply is a constant, obviously, yeah, times. I mean, it's not it's not dependent on velocity. What I meant, yeah. B times xi plus not plus in the exponent c times xi. So this is how the equilibrium is supposed to look like. Yeah. So what we now have to do is according to what we actually have. Yeah. So what is the mass? What is the momentum and the energy? We have to identify A, B, and C, right? And when we have this, we can write our equilibrium. So the equilibrium, A, B, and C, yeah, mass, momentum, and energy. So, and then this can be used to model the collision, and with a single relaxation time, as I introduced on Monday morning, there have been these people, Bhatnagar, Cross, and Krug. In 1954, they wanted to solve this integral for the Boltzmann equation, not necessarily for the lattice Boltzmann equation. And then they said, okay, so what the collision does, it brings the distribution function closer to the equilibrium. Now this is a model. Now suddenly, so up to this point, we talked about the equilibrium of the entire universe. Yeah. So now in this assumption here, we talk about the local equilibrium in this particular area. Yeah. So this is we suppose we have this. You remember we have this event horizon. So for a very short time, everything we know about the universe is in a small volume around us. Yeah, and in this small volume around us, we'll have a certain number of particles, which is our mass. We will have a certain momentum in this small area, and we would have a certain energy. Yeah? That would then define our local equilibrium. And what collision then does is it would drive the setup of the particles toward that local equilibrium. So this is the idea, and this is then often expressed in df. So this the collision operator as a derivative of f with time is then driving the equilibrium, driving the population into, or the distribution into equilibrium given a time scale tau. So you remember yesterday I wrote omega. There is a little bit of reason that has to do with lattice Boltzmann why I write there omega. We'll come to this a little later. In the original model, there was a tau. So I said omega is a frequency, so it's kind of inverse of the tau, but not quite. And the not quite we get a little later. Okay. So this tau, this is the relaxation time, and this is related to the mean free path. To the mean free time, of course, between collisions. So I've been told not to write in the lower right corner. I always forget this. If we now integrate this, so we have after collision at t plus a time over which we integrate, then we would have this as, the starting value plus the integral from t to t plus delta t over the collision operator. Yeah, so the change in this, and we integrate this over tau. So this is how we get, how we would originally integrate this and see what happens over, you see this tau, this is not tau, this is I have to get a t, a different t that is distinguished from that t. Yeah, it's not tau, because tau is the parameter here. Okay, so now this obeys all the conservation laws. We have to check this. I mean, it's kind of trivial that it's okay. I don't know whether it's trivial, but we can discuss why this is always the case. So conservation laws. So what happens with mass? So in order for this to obey the conservation law for mass, we have to do this integral. Yeah, so where we basically compute the mass of f, and we compute the mass of Fiq. Yeah, and because by definition the mass of Fiq is the same as the mass of f, right? So if we do the integral of both and subtract them, they will give us 0, and this means that this this collision operator does not change mass. Yeah, so we add something that does not change mass. The same momentum. So what do I have to do with this integral in order to compute momentum? I want to compute momentum, so of this collision operator. So what do I have to add here? Xi, right. So I have to integrate over Xi, and now I get the momentum of F and the momentum of FIQ, and I subtract these two integrals, and I get 0. So energy have an integral of FEQ minus F divided by tau, and now, what now? Psi dot psi. By the way, I mean, don't feel shy now. Everybody clear why this is? Okay, we'll talk about moments a lot. Yeah. So these are the moments of the BGK operator. Okay, I'm repeating myself with introducing moments, but we really have to have a good understanding of this. So moments are integral properties of a distribution. So one thing that we are using them for here is that they give us a transformation of our statistical variables to okay, I'm reluctant to say continuous. You know, because statistical variables can also be continuous, but to the primitive variables that we know from continuum physics, like, you know, momentum, velocity, yeah, and temperature and these things. Yeah, so these are all obtained from physics, from physics, from integral, from moments of these statistical distribution function. And now comes an important definition how we can systematically obtain these moments. And for this, we say that we take F, capital F, of capital Xi as the bidirectional Laplace transform of F, of the distribution F. F of small xi. So bidirectional Laplace transform. The same thing can also be done with the Fourier transform. So Fourier transform and Laplace transform are in that sense the same. Just the Laplace transform is a little bit more convenient to write down. Okay, I'm not sure that everybody is as familiar with Laplace with integral transformation, but I hope you have heard about the Fourier transform at least. Laplace transform you use for solving differential equations. Yeah. So we'll define this, even if now suppose you don't know, yeah, then I define it that way. So bidirectional, because Laplace transform usually integrates only from 0 to infinity, and bidirectional now means we are integrating from minus infinity to infinity. The function f of xi times the exponential function in xi, small xi times a capital Xi. So this capital Xi is what you could say the frequency of velocity. Yeah. So it's the inverse variable to the velocity variable, and we integrate this over all Xi. So what when you're familiar with this jumps into your eye is that usually you would assume that this is e by the power of minus Xi times Xi. Yeah? Anybody notice that? Yeah. Here we unfortunately we have like the sign convention is the opposite to the usual convention. I don't know why this is the case, and it leads to a lot of confusion, and it also leads to a lot of errors in my papers. Yeah, because I then have it written it down the usual way and using it the other way. The thing, I mean, you could also do with the other sign conventions, but then all velocities in the universe would, everything in the universe would walk backward somehow. Yeah, that's it's this kind of the chirality problem. But it's okay. So this is how it was. So this is how it comes out at the end with the right sign. So this uses a frequency Xi, which ugly enough we take as Xi capital Upsilon. You know, I know that I cannot write these letters myself, and a capital Zeta. Yeah. So good thing that I'm getting recorded. This is the same as with eta. Yeah, this is a letter that looks like a Latin letter. Yeah, but this is supposed to be a capital Zeta. So why do we do this? We do this because this capital function now is the moment generating function. It's the moment generating function. So that means we can generate moments, I call moments M, with indices A, B, and C as this chain of derivatives. So we take the ath derivative of the first component of this vector, the bth derivative of the second component of this vector, and the cth derivative of the third component of this vector onto f of Xi, and then I evaluate this after I have this at velocity, no, not at velocity, at Xi, the frequency 0, and then I get the moment. Yeah? So if you look at this very hard, then you see, so okay, we get increasing derivatives, and we evaluate this increasing derivatives at a certain point, namely 0. Yeah? So then you should be reminded of another place where you do these things. You should be reminded of the Taylor series. Yeah? In a Taylor series of a function, we take increasing derivatives and all evaluate them at the evaluation point. Yeah? So the only difference is that you also have a prefactor in front of this. Yeah? But if we ignore the prefactor now, you see these are the coefficients of a series expansion of f. Yeah? So basically, what these moments are the increasing coefficients of a series expansion of the Laplace transform of the distribution function. This is what they are. And I mean, if you're familiar with integral transformations, you will notice something interesting here, namely that these are continuous functions. I mean, think for a moment back to how matter is actually made up. Now we could say we're dealing with a probability density function. This probability density function is continuous, so we have continuous variables, right? But you can also think in another way. We have atoms flowing around. These atoms, they are all discrete things, or molecules. They're molecules are flying around. Yeah, so they are all discrete things. Now, what happens if you take the Fourier transform of a discrete function, a Fourier or Laplace transform of a discrete function? You get a continuous function, right? You get a continuous function, which is also important because this means that even if you have a discontinuous function, you can compute moments out of this because you can only make a series expansion of a function when they are continuous, or at least piecewise continuous, right? So these moments are well defined even for discrete functions, and they are continuous even for discrete functions. Yeah? So interesting thing. So there's actually, actually now it makes sense if you think about it, that you have molecules flowing around. They are all discrete things. Yeah. But you can describe them with a continuous field in the Navier-Stokes equation. Yeah? Why is this the case? Because these field variables in the Navier-Stokes equations, they are moments, and moments arise from taking the Laplace transform of even a discontinuous function, which gives you a continuous function, and then making the series expansion of this. So you deal with continuous function. Yeah? So it actually makes mathematical sense to describe the discontinuous world with discontinuous functions. Yeah? Okay. Where have been? Yes, I should write this down. So these are the coefficients of a series expansion of f of xi at the development point. So the development point for the series expansion is at xi equals to 0. So we go a little bit through this pain because this is something that you will most likely not see in most of the papers and most of the books. Yeah. So most of the papers and most of the books will start from a drastic simplification of this. Yeah, but you should know where things are coming from, because only if you know where things are coming from, you really understand it and you really can make a change. Yeah? So, because now when you end up looking in a book, you just see the simplification that we are now going to derive. So for this, we use xi again. The individual x's is of this vector is xi, small upsilon, and small zeta. And do the following. So we have this MABC is equal to, okay, write it again. It's annoyingly a lot to write. Zeta by the power of c. So we integrate from minus infinity to infinity over f on xi and e xi by xi at xi is equal to 0 and integrate this over xi. So now if we track these derivatives into this here and we take the derivative of this exponential function, we'll end up with having obviously, okay, we take the derivative of an exponential function a times is extremely difficult. Yeah, gives us xi by the power of a, obviously, right? And upsilon by the power of b and zeta by the power of c. Everybody agrees? I guess so. So, and then this here is left. And this is evaluated at 0, and because it's evaluated at 0, actually the thing here will give us a 1, yeah? And our integral simplifies to this one, where we just integrate over this product. Yeah, so we don't need to have, we kind of don't need to bother anymore that there is a Laplace transform in between in the definition of this. Yeah, so we just multiply this with the distribution with this function here and integrate, and then we get our moment. And this is usually what you will see. Now we call these things, do I write this on the same page? We call these things countable Ra moments. So why countable? Countable because we have A, B, and C, and we can count up A, B, and C. It's not one-dimensional countable, but it's countable in 3 directions. Yeah? And Ra, we call this Ra because they are in the lab frame, or if we prefer this Euler frame. So now these are only one possibility of getting to moments, but it's a very structured one. Funny enough, it's not the one that was originally used in the Lattice Boltzmann method, but now I think it's becoming more common. So, okay, not necessary for everything, because these moments, as a mathematical definition, may have some disadvantages. Yeah. So you could also, so there's one clear question that you have: what is the frame of reference? So what do I mean by frame of reference? So this f is a function in velocity. Yeah. So if we give it a function in velocity, we also have to define. We always have to define velocity compared to what, right? So we can only give a velocity of something compared to something that we define to be at rest, which is what we call then the lab frame. So there is some lab, there is some desk, and the desk is at rest by our definition. And this is usually not a good definition if you deal with fluids. So in fluids, you would rather say, okay, the thing we take as a reference frame is the center of mass of our small little universe in which the collision takes place, right? That would be a better definition, probably. So then there are the orthogonality conditions that are going to bother us a little bit later. And then there's all sorts of normalization. I mean, moments, you can always scale moments by multiplying with constant factors, yeah? So the frame of reference is one of the more important things. Could write more nicely. So the frame of reference, I've already mentioned this. We have Eulerian and Lagrangian. So Eulerian, the laboratory frame, So we have a stationary observer. And here we have the material frame. Which means we have a moving. I mean, it's not only moving, but it's moving with the object. So, and now by definition, we call the Eulerian moments, we call them raw moments. And the moments that we take in the Lagrangian frame, we call central moments. Yeah, so these two things you need to be very clear what their difference is. Okay, let's try to get this a little bit understood. So suppose we have this distribution function f, which is a function of now one-dimensional xi, where xi is equal to 0 here. And let's say this function kind of looks like this. And here is velocity. Here we would have the velocity u. Now you see that the center of this distribution is not around 0. Yeah, so we would say by integrating over this, the velocity, the macroscopic velocity here is u, right? Now we can shift our distribution function by u. So fu is the original f of xi plus the velocity u. Yeah, so we make what we call a Galilean shift. Yeah, we add to the velocity the center velocity. So then we are, so the black f is the Eulerian and the red f is now in this Lagrangian frame, yeah, because it's moving with, it is centered in the distribution. So when we look at our original definition, and there you see this is a good thing that we have our original definition of the moments here. So we do the Laplace transform of f of xi plus u e xi times c dx xi. So we do the Laplace transform of the shifted population, of the shifted distribution. Okay, now how can we rewrite this? Notice that we go from minus infinity to infinity, right? So if I want to get this u out of here, I could shift these boundaries, say by u. And if I add u to infinity or I subtract u to infinity, it's still infinity and up infinity and up infinity. So what I can do simply, so the only thing that is happening when I'm replacing this, when I'm shifting this xi, is that I have to shift it wherever it appears. Like it appears here and it appears there, right? So then this is the same as writing f of xi, yeah, by e by xi minus u times xi, this integrated over xi. So, and now if I simplify this again the way that we had it, then I can write the so-called central moments, which I always write with a k for whatever reason, as now the integral over f of xi minus u by the power of a upsilon minus v. So I'm using u, v, w as the velocities by the power of b, and xi minus w by the power of z dx. So what we get into the moments is, we started with shifting the distribution by adding the velocity. Now, in order to compute the central moments, we have to subtract the velocity. Now these we call the central moments. Central, okay, let's write central countable moments, because we can also count them up with A, B, C. So now, by definition of the central moments, we have K1, 0, 0 equal to what? Who is following me? K100? Always. It's the velocity, right? So it's the velocity. What is the velocity in the center of mass? I kind of hear it, but you need to be more confident. 0. Yes, this is 0. Yeah. So this is you centered your distribution function, and you're asking for the first moment. So the first moment is the bias, if you think statistically. Yeah? If you are centered, by definition, your center is at 0. So this is the same, of course, for all the 3 different directions we are dealing with. And they are all 0. So regarding the density, we say that the density is Galilean invariant. Galilean invariant means that something is not dependent on the frame of reference. And indeed, M00 is equal to K000, right? And this is, we call this thing the zeroth moment. And because they are countable, they have an order. And the order of moments is equal to the sum of its indices. Indices. Okay, I'm obviously too stupid to write indices. Yeah, you just write indices. So we've seen there is 1 zero-order moment, and there are 3 first-order moments. So first order because the sum of these indices are always 1, right? So how many second-order moments do we have? Give me a guess. Do we have 3 second-order moments? Do we have 4 second-order moments? Who is for 3? Who is for 4? Who is for 6? Ah, okay. We have 6. We have 6 second-order moments. So there's a question of permutation. Yeah, we have M200, M020, M002. Now these are all second-order moments, but we also have M110, M101, and M011. Yeah? And these are all the permutations that we can produce, right? So there are 6 out of them. So the temperature can be written as a combination of moments. So if we want to write them in terms of raw moments. So, temperature is intrinsically not a raw moment, it's a centered moment. So what we have to do is we have to have the mass of the particles, the density, and the Boltzmann constant, and we have to integrate over the entire velocity field. Not velocity, the velocity space. So, and now it's actually, you see, a second order central moment, because what you have to do is you have to subtract the velocity of the particle. So you would count this as kinetic energy, yeah, and only when you are in the frame of the stuff, and then you measure their movement around their average position, then you would count this as a contribution of thermal energy. Yeah, the other thing you would count as kinetic energy. So it's actually more naturally a central moment. So if we do this now in order to see how this turns out. So this is not a C. This is supposed to be a rho. So my rhos and my zetas all look the same. I'm very sorry. So so we are doing this in order to kind of understand how to split moments apart. Yeah, so first of all, we have to do this scalar product here. So we get Xi, so Xi second order is U Xi, U times Xi plus U times U, big C. Okay, so why are we doing this? We are doing this because, I will write it out now, but we'll see that this here does not depend on Xi. Yeah? So it will basically give us a zero moment. This here depends on Xi once. This will give us a first moment. And this here depends on Xi twice. Yeah, so this will give us a second moment. So we'll have second, first, and zero moment in the same thing. So let's see how this turns out. Maybe a little bit, lot of writing here. Okay, I let Xi out of F because this is now known. So if we take this the scalar product any further, then we have Xi square, Xi square, upsilon square, zeta square, and then we have minus 2 U Xi minus 2 V upsilon minus 2 W zeta plus U square plus V square plus W square, and this integrated over Xi. Now, if we do the integral, so we get one moment for this, because this is multiplied with F, one moment for that, and one moment for this. So we can write on the next page that this is equal to m divided by 3 rho Boltzmann constant. So integral f Xi square gives us m200. Upsilon square gives us m020. Zeta square gives us m002. Now minus 2u. U is not the function of zeta, yeah? Of Xi, zeta, or upsilon, so this will stay here. And now we integrate only over Xi, so this will give us what is it, M10. M10, the next is minus 2V M010 minus 2W M001 plus, so now there is nothing, no Xi, zeta, or upsilon in it, so it's just U square plus V square plus W square into now M, what? 0, 0, 0, right. So this is actually rho. Yeah, M000 is rho. M100, because we have not normalized it, is a rho times u. M010 is rho v. M001 is rho w. And if we combine all of this, we get T is equal to M divided by 3 rho K Boltzmann. So now what you observe is this becomes U squared times rho. Yeah, the same thing that we have already here. Yeah, but we have it here twice and here only once. So meaning that we get M200 plus M020 plus M002 minus, we can just write U times U, right, times rho. So this is the kinetic energy. Yeah, this is the kinetic energy that we have, and this is the thermal energy. Of course, in central moments, it's much simpler. It's M3 by rho K Boltzmann, and we have it K200 plus K020 plus K002, because this is exactly, what was the definition. Okay, I told you there will be a lot of moments here. Now, we still have, okay, it's, what was it? Yes. Now, we do this because moments, in the end, we need the moments of the equilibrium. Moments of the equilibrium. So, and here we use this Maxwell-Boltzmann equilibrium. This is what Maxwell and Boltzmann derived. So Maxwell knew what it was, and Boltzmann proved that this is true. Also, it goes the story. So it looks a bit like this. So there is the temperature also in front by the power of 3/2 E by Xi times Xi m by 2kB T. Okay, so you already noticed this is when velocity is 0, yeah, because otherwise I would have to subtract here Xi times Xi minus U times U, yeah. Okay, so this can be written as obviously rho 2 pi K Boltzmann T divided by M. So M is the mass of the particle by the power of 3/2 E. Now we can split all of this apart. We'll in a moment see what this is good for. So divided by 2K Boltzmann T E minus this is supposed to be epsilon square M 2K Boltzmann T times E minus zeta square M 2KB T. Okay, now we take moments of this, and the idea, I want, now this is going to be a little bit a longer calculation, maybe some of you had the impression that we do longer calculation all the time here. This longer calculation will make our life later much simpler. Yeah. So the thing is, we don't want to go through the integral of this function for all different moments, but we would actually like to see a relationship between the moments in equilibrium that simplifies how we can calculate them. Yeah, and this the idea behind this distribution function, the equilibrium distribution function, the important thing is that the different components, so the x velocity xi, the upsilon velocity, and the zeta velocity, they do not appear together. They only appear in the scalar product, but there is no cross correlation between them. For a random, for a probability of finding something, because this is a probability function. What this means is that the equilibrium means that if you pick a particle and you measure the velocity of this particle in y direction, and you are in equilibrium, then by knowing the velocity in y direction, you know nothing about the velocity in x direction, right? This is so. This is, no mixed information. Yeah, that's the idea behind this equilibrium. Yeah, so and this is a property that we can use in order to drastically simplify how we compute the equilibrium moments. But for this, we now have to go through a little bit of calculation to see that this is actually possible. So now we take the moments of this, yeah, and important thing is this is only true for the equilibrium. Because if we are not in equilibrium, yeah, there may be a correlation between the x and the y velocity. Yeah? There could be any correlation. So let's say we are taking this integral with this prefactor, this nasty prefactor. bt, I should actually try to remove this. So, and e by the power of, now this is not a mistake, it's not a vector, it's the xi component, divided by 2kb t, e minus upsilon square m 2kb t, e by minus zeta, not xi, zeta square m by 2kb t, and this is into xi by the power of a, upsilon by the power of b, and zeta by the power of c d, and this is integrated over the entire xi. Now, what we can do now is we can separate out everything that just depends on xi, on upsilon, and on zeta, and rewrite this integral, this 3 times integral in a different way. So something that does not depend on anything, of course, can be put in front of the integral. Then we write all the 3 integrals, and we go the outer one will be the xi integral. Now we call this e by the power of minus xi square m divided by 2k Boltzmann t times xi by the power of a. So now we have everything that depends on xi put together. Yeah. So the rest does not depend on xi, so we can put here okay, we can put the next integral here as e by the power of epsilon square m divided by 2k bt epsilon square, and closing the brackets and going on the next integral and integrating over the theta part. Now this is supposed to be theta square m divided by 2k Boltzmann t, theta by the power of c, and now I integrate this over theta. Now so you see what I'm going to do. I'm integrating this, only this over theta. I'm not integrating this over theta because there is no theta in it, so I can put it in front of the integral, right? So, and then I integrate the next thing over epsilon and the last thing over xi. Now, because these things all not depend on each other, I can actually tear these integrals further apart by saying, I hope I'm not too trivial here, yeah, because everything of this, where this is going, could also be obvious to you, but I thought we go through this anyway. So I can put these things apart. This is supposed to be xi. Cm square, of course, 2kbt times xi by the power of a, and I integrate this over xi. Yeah, so everything. So I'm only doing the integral over xi because this is the only thing that depends on it, and here I integrate only over epsilon. Write a proper epsilon. M 2k Boltzmann t epsilon b, so all over epsilon. So, and then this is multiplied again with the integral over the theta part, e by the power, should close the bracket if I open a bracket. Was not necessary the bracket, okay. Theta square m 2kbt and theta by the power of c, and I integrate all of this over theta. Okay, now I've tiered these things apart. So and we see we can maybe I should rather have this brackets here, yeah, to see that we can actually multiply these things out. So it already looks like we can actually factorize these moments. The only thing that doesn't work out here very well is that these are integrals only over one component, and the moments are the integrals over all components. So we have to extend this a little bit. And in order to do this, and this is actually an important part of this, what we do is we take the left-hand side of this, MABC equilibrium, and divide it by the moment M000, right? And this moment M000 can be split up in a similar way to the others. So we'll have the integral just over xi. I should try to find a more efficient way to write all of this. CAD xi. So what I'm doing is I'm splitting up the integral where a is equal to 0, because, I mean, what is the difference? Now a is equal to 0 in this integral, right? So I can split this up here just with a being equal to 0. So I'll just have a equal to 0, and I divide by this, so times the integral over e minus epsilon square m by 2k Boltzmann t. Here comes epsilon by b integrated over, not over xi, but over upsilon, divided by the integral over the same thing, e upsilon square m, 2k Boltzmann t, and integrated over upsilon. And this is then again multiplied with the integral over e minus zeta square m durch by 2k Boltzmann t zeta by the power of c integrated over zeta divided by the integral over minus infinity to infinity e by the power of zeta square m 2k Boltzmann t over zeta. So let's now pick out. Okay, what I'm going to do is I'm just picking out this guy here. And say that the integral over this e minus c square m divided by 2k Boltzmann t xi a dxi divided by minus this e minus xi square m divided by 2k Boltzmann t into xi. So this would basically stay the same if I added, I leave some space here, if I added the parts that are not in here, so upsilon and zeta, 2k Boltzmann t, multiply this from the outside minus this and this e minus zeta xi squared divided by 2k Boltzmann t over xi and zeta xi a d xi. So, okay, I'm missing some space here. So I can also multiply the same thing down here so that we basically get kbt, nothing changed, e m by 2kb, integrating this over xi. And now I can integrate. So, okay, so nothing changed according to this, yeah, because we just added it on both sides. And since we have nothing changed, we can also integrate this above and below. Yeah, will also give the same thing because it's not changed over upsilon and zeta, the upsilon and zeta. And I hope I did not kill you with all of this. But the result is that this gives us ma 0 by the power of b divided by m0, 0. Okay. Why am I doing this to you? I'm doing this to you sorry, b. This is nonsense. Equilibrium, of course, right? So why am I doing this to you? I'm doing this to you because what we have just seen is we can split this up and we get for the first part ma0 of equilibrium, this is important, divided by m0. 0. This means we can always write MABC equilibrium divided by M000, yeah, because this is what we originally calculated, as MA00 equilibrium. So this was the first part divided by M000. This is what we had here. And this came from picking out the first. Yeah. Now we could do the same thing to the others, seeing that we get M0B0 equilibrium divided by M000 times M00C equilibrium divided by M000. Okay? So this means we need to know the equilibrium only in one dimension in order to calculate the equilibrium in all the, all the mixed moments. Okay? So this is the reason why I tortured you with this integrals. Okay. Few more things. So okay, so this is we only need to calculate equilibria for one-dimensional moments in order to get them for all the different. So we have one more. So the thing was we get, what was it? Was always said 1.5 to 2 hours. So today we'll have a little bit more than 1.5 hours in the morning, because we have one more topic that will also be of importance for the rest of this lecture. Yeah, and this is the orthogonality. So later for the lattice Boltzmann methods, you'll see drastic differences in performance depending on the way you define your moments. And this is why we spent so much time before that on the theory of moments. Yeah. So, and one of these properties that has drastic influence on the stability are the orthogonality properties, and these can be done wrong and right, and in different ways again. So the basic idea behind this is that we like moments to be independent of each other. So for whatever reason, humans, is there anything of that may be strange to repair? No. I often make mistakes, so don't hesitate, to call me out. Okay, so for whatever reasons, humans like to be independent, like independence, right? So why would we like independence of these moments? So we have seen the BGK operator, where we have only one relaxation time for everything together. So the reason why we split these things up into moments is that we want to give different operations different weights. Yeah. So interactions between many particles should be less common than interactions between few particles, for example. Yeah. Now, in order, so this would imply that we attach different relaxation rates to different moments, for example. Now, is this possible when two moments are somehow correlated to each other? When they are physically correlated, yeah, they should also always evolve on the same time scale, because how can something, they would have to follow each other, right? So in order to separate their time scale, they also have to be uncorrelated. Yeah, so they have to be independent of each other. And one of the big questions is how we how we can actually do this. So, and would they be automatically independent of each other? Now let's have a look. Let's have this example. We take M200 equilibrium, which we get when we integrate this thing here that we have now written so often, minus xi times xi m divided by 2k Boltzmann t xi. So we multiply this by xi times xi, integrate this over xi. And then there is a difficult integral, which I prefer to solve with Mathematica. And Mathematica gives me rho k Boltzmann t divided by m. This is what Mathematica told me that this thing is. Now, let's look up what is the moment M400 is. So we have to write all of this again. Minus xi times xi m divided by 2k Boltzmann t. And now it's supposed to be the forced moment. So the forced moment is 4 of them together. Now I ask Mathematica, what is this supposed to be? And what comes out is k Boltzmann t divided by m by the power 2, and also with rho. Okay, now what we observe here is that this is more or less the temperature squared. And of course, this is only an example that should highlight that the moments, unfortunately, they are not independent of each other. Yeah, not even in equilibrium. There's also the different question: when we are not in equilibrium, are they then independent of each other? But here we see that the second moment is the temperature, and the fourth moment is the temperature squared. So they are not, obviously not independent. And the trouble is, this is the same. This is the same for many other moments too. So how can we then make them independent of each other? And actually, this is kind of a little bit a controversial topic, because before we can say that something is independent, we have to make a proper mathematical definition what we mean by that. And this is kind of a little bit missing. Okay, so there had been this idea that we simply make this function orthogonal to each other, and then they would be independent. So what we mean by orthogonality? Also, by orthogonality, you can mean different things, unfortunately. Say we have a moment m defined like this. This is f times a function phi m integrated over xi, and n is an integral over f with phi n. So there are two different moments. And now the moments m and n are orthogonal with weight. Okay, now we have also weight. So the weight depends on the velocity if the integral over the weight and these two functions that define our moments, if this is zero. This is orthogonality. Now, this is not a unique definition of orthogonality. I mean, it says there can be a weight, yeah? And so what you define as orthogonality depends on the weight. In the original lattice Boltzmann methods, these weights were simply set to 1, and it took almost 2 decades to understand that this was a big mistake. Yeah? So hopefully you understand this in 2 weeks and not in 2 decades here, yeah, because this is essential part of what we are going to learn. Okay, so one thing that came a little late in lattice Boltzmann, but kind of works, is to choose this weight according to the so-called Hermite moments or Hermite polynomials. And the idea here is that things are supposed to be orthogonal at equilibrium. And this means that the weight is the equilibrium. So we know the equilibrium looks like a Gauss function, yeah? And Hermite polynomials are polynomials that are orthogonal with respect to this Gauss function. So then it appears to be logical to take moments according to the Hermite polynomials, because then they will be orthogonal at equilibrium. So with weight equilibrium, yeah? So saying that F equilibrium of now, okay, I use X here because this is general and is not necessarily only for velocity space. This is now any space. Yeah, it's not supposed to be spatial space here. So the equilibrium function for this is supposed to look like this. So we have e by the power of minus x squared divided by 2 sigma square, with sigma being the standard deviation of this Gaussian function. And x in this case here is our random variable. So I want kind of to say that Hermite polynomials and Hermite moments have not been invented for lattice Boltzmann. Yeah, so they can be used in other contexts too, where your distribution does not deviate strongly from a Gaussian function, which is a very common assumption about many things in statistics, right? So the Hermite, polynomials, Hermite polynomial of degree n would now be, so this zero order the zero order would just be 1, so this would be the same as the countable moments for first order, it is x scaled by sigma square, and phi 2 is x square minus sigma square divided by sigma 4. Phi 3 is x cubed minus 3 sigma square x divided by I just noticed that I've forgotten how the derivation of this is. So okay, you can look the derivation up on presumably also on Wikipedia. So these are the moments. Sorry, not the moments, the polynomials to generate the moments. We'll have an example in a minute. X squared plus x4, divided by sigma to the power of 8. So, okay, here again it is that because we use a Gaussian function, multidimensional Hermite polynomials factorize. So say we have this polynomial phi, okay, we start with n and ml, so these are the indices for x, y, and z direction, yeah? And now they depend on, we would do them for xi divided by sigma, upsilon divided by sigma, and zeta divided by sigma. Then this can be written as phi n of xi divided by sigma, phi m of upsilon divided by sigma, and phi l of not xi of zeta divided by sigma. We can also define central Hermite polynomials. This is also used for lattice Boltzmann, central Hermite polynomials. Phi, so this should be the central Hermite polynomial. Can be written in usual Hermite polynomial just by subtracting, the bias. So this would be here v minus upsilon divided by sigma times phi l zeta minus w divided by sigma. So now, as an example, and this is the last thing for this morning, what am I writing? We apply this to M400, okay? So first of all, we need the variance. The variance, so sigma square is M20, is a second moment minus, it's actually a second, the variance is a second central moment, right? So we have to subtract the bias square here. Since this is a little bit nasty and the calculation is long anyway, we assume for simplicity, so we set the velocity to 0, right? So that sigma is just sigma squared just turns out to be kBt divided by m, which is m200 divided by m000. So then calculating, so we take m400, which then is 3, so we have to plug in the sigma, 3m200 square divided by m000 square minus 6m200 divided by m000 xi square plus xi by the power of 4, and all of this divided by m000 to the power of 8. Now when we want to compute, so I will now call this first order Hermite moment. I will just put a snake on its top to distinguish it from the usual countable moments. Yeah? And calculate this integral of the equilibrium function kbt, okay, then see it's kbt by m, and this to the power of 3/2 e by the power of xi times m divided by 2 k Boltzmann t. Now comes this entire thing here, 3m200 square. So the moment is already in here, so this is a constant now as far as the integration goes. m200 divided by m000. Now this goes into xi square, and then there is a xi by the power 4, and all of this is divided by m200 by the power, oh, sorry, 200 by the power of 8. Did I sigma? Okay, I have to agree that this, okay, I apparently made a mistake here. This must be 2m200 by the power of 8 and m00. I did not take a lot of attention to this because later it does not, it will disappear. Okay, this integrated over xi. So what you see here is that this here gives you a zero order moment because there's no xi in it. Here is a xi squared, this gives you a second order moment, and here this gives you a first order moment. So we have this combination of zero order, second order, and third order moment in this, and will turn out to be 3 times 3 times m, so zero order moment, 3m m00, 2m0 to m000 square minus 6 m, now the second order moment, m200 times m200 divided by m000 plus m400, and all of this divided by what I just corrected, m200 divided by m00 divided by the power of 8. And if we plug all the values into this, then we get here 3 times rho kBt by m square. So this is the moment m20 by divided by M002, yeah, and square, and multiplied by M000 minus 6 rho KBT M also square. So now we had M200 square, M200 square, and plus what we had before, 3 rho KBT by M. So this is what we squared. This is what we just calculated for the original moment. And now we divide everything here by M200 divided by M000 divided by the power of 8. So now what you see is we have 3 and 3 minus 6 gives us 0. This definition of the Hermite polynomials, yeah, I didn't have it with me, so I write it down here again. So there are actually different definitions of Hermite polynomials. The one that is suitable for us is this one here, where phi n. So the end Hermite polynomial of x divided by sigma is minus 1 by the power of n, the e function ex square divided by 2 sigma square times the nth derivative of e by the power of minus x square 2 sigma square. So you will also see a version without this 2 here. We expect from an independent moment to be the case, right? So since the equilibrium only depends on the conserved quantities, yeah, we want an independent first order moment to depend on nothing, and then it can actually be only 0, right? And these Hermite polynomials have the property that for the equilibrium, these moments are all also orthogonal to each other. The problem being that we are not actually dealing with things that are always in equilibrium in the Lattice-Boltzmann method, or that are necessarily very close to equilibrium in the Lattice-Boltzmann method. This is why we have to do something even more clever to get everything out of the system.